Thank you. This afternoon I'm going to try to talk to you about some research we do in the physics department on terahertz, this portion of the electromagnetic spectrum that, as this newspaper headline suggests, might allow us to see through walls and through clothes, very similar to X-ray specs from the old Buster comic in the 1980s that many of you may be familiar with. The terahertz part of the spectrum is sandwiched between the microwave and the infrared, how your TV remote control or how your microwave cooks your dinner. It's an interesting part of the spectrum to do, particularly astronomy that we're interested in, but many other applications as well. It's not very well utilised because effectively the radio technology on the right, on the left, and the optical technology on the right, those two technologies haven't really converged to this part of the spectrum. So it's very novel, very new, very unexplored. In the physics department, we're quite interested in astronomy applications, but there's lots of terrestrial applications. And in the week where the CIA have found in the underwear bomber, terahertz radiation, if you had a terahertz camera, you could see through people's clothes and you could see concealed weaponry, etc., underneath their clothes. These type of full body scanners are being rolled out through many airports. There's lots of medical applications, a cross section of a tooth decay. You can see through a matchbox, see matches inside for quality control. You can see a bar of chocolate here, a terahertz image. The impurities inside the chocolate show up. So it's very interesting. You can see through objects with this. For astronomy, if you look at the sky using this part of the electromagnetic spectrum, we actually observe different kinds of objects. We observe the cold universe, star-forming regions like around the Orion constellation here. Just recently, the European Space Agency launched this satellite dedicated to observing in this part of the spectrum. I was lucky enough to work on this. I'll talk a little bit about that. And also there's an exciting project called ALMA, which is being built in the desert in Chile to do some astronomy from the ground as well. Why astronomy at this wavelength is very interesting is that half of all electromagnetic energy emitted by stars and galaxies is now observed in this part of the spectrum due to the expansion of the universe primarily. So we look at the cold universe, we can see the chemistry of the universe, and we can see very interesting things. This European Space Agency mission I've worked on for about 10 years now. It's a very large satellite instrument. It was launched in May 2009. 3 different instruments. We work primarily on one instrument called HiFi, H-I-F-I. And it's effectively a very high frequency radio receiver. What do? We do the optics, so we design optics, we test optics, we validate the optics for the instrument. There's a telescope, there's some intermediate optics, and there's some kind of antenna then with a detector. We're looking at very, very weak signals, so we need very, very sensitive instrumentation. This is HiFi, it's about this big, and this is some of the optics. It's a little bit like an optical telescope, a little bit like a radio telescope, so we need electromagnetic analysis to be able to deal with it. Here's some mirrors here and a little antenna showing across there. What we did was, very interestingly, we were in the design phase from the early 2000s right through to the flight test model, and we qualified the optics, make sure the optics of the instrument was designed, manufactured, and experimentally tested correctly. It doesn't actually image, it actually produces spectra, and this is a spectra of the interstellar medium, and we see very complex chemistry that was never observed before, things like water lines, formaldehyde, methanol, very complex things that were previously never seen. From the ground, this is the most expensive project in astronomy in the world at the moment, ALMA, the large Atacama large millimeter array. 66 12-meter antennas all working together to form a very important composite image at these terahertz or infrared wavelengths. They all have to be moved around in the desert, so they've got these 18-wheeler trucks to move these 100-ton antennas all around the desert. And within the body of this telescope here, cryogenically cooled receivers look at the very cold universe that we see. And again, in Maynooth, we've been working on the optics that are squashed inside this large, sophisticated blue fridge that cools everything down to a fraction of a degree above absolute zero. It's the most expensive project involving all countries in the world. It's costing billions to actually put together. Going to the future, we've also trying to build at higher wavelengths and higher frequencies. Speak Far is a mission that's going to be launched in about 2020, so it should take me through another portion of my career. This is a horn antenna array here. In the lab, over in our experimental physics department, we try to do some measurements as well as all these simulations that we do. We work around 100 gigahertz, which is about maybe 50 times your mobile phone frequency. With this expensive piece of kit called a vector network analyzer, it allows us to do very, very sophisticated measurements, allows us to develop our analytical techniques that we have to develop from scratch because no commercial software is actually available to do it. And this is how the kind of regime of this terahertz development needs to be understood. So in this very, very brief time, and so it certainly felt that I hope I've given you some overview of why this little part of the electromagnetic spectrum might be useful and what we do in the experimental physics department associated with it.